Good afternoon, everybody. Welcome to a nice Wednesday afternoon, a Chem 170 with your host, me, Dr. White. Hi. All right, important announcement. I was looking at the schedule, and this I do a lot of times in the first test, and that is it's scheduled for next Wednesday. Now, I could go real quick and uh, get everything done before the test. But that's not good for you. You're here to learn, not to keep the exact schedule I put on my syllabus. And usually the first test, sometimes you make it, sometimes you don't. I'd rather go at a pace that helps you do well on the test, which means you learn organic chemistry, as opposed to just keeping to what I thought would work. So I will put out an email later today or tomorrow. I'm postponing test one by 1 week. It won't be the 14th. It'll be the 21st. So test one will be postponed by 1 week. And I'll put out an email and announcement to that effect. All right. Another thing I want to talk about is labs. Labs are due the next week after we did the lab. Last Wednesday, we did the melting point. If you have not, and most of the class hasn't, uploaded the lab, you should. Let me show you how to do that, in case you're not familiar. Let me go to student view. All right, does everybody see Chem 170 on your screen? Thank you. I've got you all trained either like this or thumbs up people. Thank you. I shouldn't have said it that way, but it's true. All right, click on assignments and you'll see melting points. And for me, no, I didn't submit it, but if you click on here, you'll notice there's a place here where it says submit assignment, and you'll add a file. And this will open up an interface to allow you to pick a file from your computer. I have how to make a PDF file, or if you can open up the PDF file, the Word document that I provided, and you can type things in. If I ask you to draw structures, if you can draw it in, otherwise you're going to have to write it on paper. Now, if you don't have a printer, for the questions and any data you have to fill in, just write it on a piece of paper. You do not have to rewrite the question. You'll make that into PDF file and upload it here. And when you're done, notice at the bottom left, you click on submit. And that's how you do it. And if I click on mine, now I'm not a student anymore, you'll see for the melting point, out of 6 students, only 2 have handed it in. Labs are easy points. I don't know what it is with the pandemic, but last semester I had this problem with a couple of students, and they lost a whole letter grade that they shouldn't have because they didn't hand in labs. So get in the habit of handing in labs. You have any questions about any lab? Ask. Remember, in my class, there's no such thing as a dumb question. Not only in my class, but in my universe. So always, always feel free to ask questions about anything to me or to anybody else, really, but I don't know about other people. All right, any questions on that? Well, in that case, let's get back to double bonds. Last Wednesday, I showed you this general reaction where if you take any double bond reacted with a halogen, fluorine, chlorine, bromine, or iodine, you break the pi bond. I can go to my whiteboard, it shows it better. you have any double bond, remember, you should know there's one pi bond, one sigma bond. Pi bonds I can break like that. Sigma bonds, single bond, no, I don't. And if you react it with a halogen gas, remember X is the variable for the halogens, which are fluorine, chlorine, bromine, or iodine. You break the pi bond, and each carbon of the double bond gets a halogen. And let's do one, then I'll let you do one, because we did some, I believe, last Wednesday, but repetition helps your grade, which I think you'll enjoy getting a good grade. And I think I'm going to let you try one first on your own. If you take chlorine gas and react it with this compound, what would be the organic product or products? Remember, you don't break carbon-carbon single bonds. No, you don't. And when you're done, give me a thumbs up or shake your head. I'm done. Thank you, Christine. Thank you, Andrew. Thank you, Ignacio. Am I pronouncing your name right, Ignacio? Thank you. That makes me feel better. If not, correct me always. All right. Now, remember, when you're looking at an organic molecule, and I do this without even thinking, automatically I look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get my attention, and yours too, like, ooh, like that. I had a whistle failure there. All right, what's different? A double bond. Everything else is just carbon or hydrogen single bonds and carbon or hydrogen atoms, and it's just going to come along for the ride. What's chlorine? A halogen. It's diatomic. It exists like that. By the way, chlorine, halogen gases are nasty things to work with. I know I have in the lab. And here, X could be fluorine. In our case, it is chlorine, bromine, or iodine. And remember, you have one pi bond and one sigma bond. You break the pi bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. So here I have 4 carbons across, and on this carbon I have 2 methyls, so I'm still going to have that. Now, here are my 2 carbons of the double bond. I broke the pi bond, and each one gets a halogen, because that's what my general reaction shows me right here. So what's my halogen? Chlorine. Each one of these gets a chlorine. And then I know there are 4 bonds to carbon. So I can put in the hydrogens. Now, chlorine counts as 1 bond. If we look at the second carbon here, it's got 1, 2, 3, 4 minus 3, 1 hydrogen. We look at this end carbon there. It's got 2 lines, 2 bonds, should have 4 bonds to carbon, 4 minus 2, 2 hydrogens, and that's the product. And that's how you do it. And we did this last week, so I don't see the need to do another example. We'll do some more in the practice problems. I will finish this chapter and I'll announce it at the end of the class. Don't forget, or no, you don't know so, but don't forget, on Monday, I will do the alkenes, alkynes problem set, and you should try it before I do. All right, let's move on. Now, everything I've added to the double bond carbons has been the same, either two hydrogens or two halogens. What happens if you have something that's not the same, which is called unsymmetrical? Well, it turns out that was a very challenging problem, how to predict what the molecule you actually get. And it's important. And a very famous, one of the most famous organic chemist is the Russian organic chemist Markovnikov, and he figured it out. And he came up with a rule. Now, listen carefully. What you see on the screen, don't write down. What you see on the screen, don't write down. But the rule states when an unsymmetrical molecule, the form HA or HQ, adds to unsymmetrical alkene, double bond, the hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom that has the most hydrogens. And you hear that and you go, what? Like on the cartoons. Well, let me show you Markovnikov's rule and how to handle it. Let's see, I'll show you. I have the slide here, but I have a better way of writing it by hand. So for unsymmetrical addition, if you have a double bond, and the first one I'll talk about is HX, hydrogen halogen acid. Let me remind you, organic chemists can write a general reaction like this, A plus B makes C, or we can also write it, and we do, like this. And this also is A plus B makes C. So if I take a double bond and react it with hydrogen halogen acid, now here this is a little different. X is not fluorine, but it's the other halogens, chlorine, bromine, or iodine. And you break the pi bond. Remember, you should know double bond, one pi bond, one sigma bond. You break the pi bond, one carbon gets hydrogen, the other gets the halogen. And how do you know? Well, I used to write Markovnikov's rule and then said I spell it right. And I realized, why am I wasting all the time writing his name? I still say it and honor him, but I'll put down M's rule, shorthand for Markovnikov's rule. Well, how does that work? Well, let's take a look. Oh, the reason why you don't use fluorine up here, HF, hydrogen fluoride, is one of the most nastiest, dangerous chemicals around. It will actually, it's the only chemical I know of that will eat through glass. It's used to etch glass. It'll also eat through your skin all the way to your bone. And it's the only time in my whole professional career when I was a bench chemist, I ever refused to do a project. The research director and my boss came to me, said, well, we'd like you to work on a project with HF. And I said, no, and if you push me, I'll leave. I'll find another place to work. And because I'd already solved some big problems, they didn't. And they had some other chemist do it. He almost had a nervous breakdown working with this stuff. It was so hazardous. Whenever he worked with it in a hazmat suit, there was a technician standing behind him with the only job was if something bad happened to him, go and run and get help. And that's why you don't see HF there. All right, let's get back to our chemistry. If we want to know, and on sometime in your future, you may see this. And it says 3 points each. Give the organic product or products. And later in the semester, we will have reactions that give more than one product. This one isn't. So how do you do this? You look at the molecule, you look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, a double bond. That got my attention like that. And I'm reacting with HBr, hydrogen bromide, and that's HX. So I have a double bond. That's the only thing that's going to catch my attention because that's where all the fun happens. And reacting, remember, halogen is abbreviated by X. For this reaction, X is chlorine, bromine, or iodine. And one carbon gets CH, the other gets CX. And it follows Markovnikov's rule. And what is Markovnikov's rule? Well, the carbon of the double bond with the most hydrogens gets the hydrogen. The other carbon of the double bond gets the halogen. Let me say it again. The carbon of the double bond with the most hydrogens gets this hydrogen. The other carbon gets the halogen. Now, I can still remember, oh, this was long time ago, that my instructor, Dr. Shuga, I think it was, he taught us that, and he said a better way to remember it is the rich get richer and the poor get poorer. We're talking about hydrogens. And he also taught us, well, if you don't like that, you can use them that has it gets it. And we're talking about hydrogens. So let's take a look at what is the product. Do you break carbon-carbon single bonds? No. So I'm going to have 3 carbons. Notice I break the pi bond, because that's what this shows you. Here are my 2 carbons of double bond. Which of these 2 carbons has more hydrogens? Now you have to use your high-level math skill for organic chemistry. This has 2, this has 1. What's the greater number? And time's up. Hopefully you pick 2. Markovnikov's rule says this hydrogen goes to the carbon with the most hydrogens. The other carbon gets the halogen, in this case bromine. And there are 4 bonds to carbon. And that's the product you get. Now, it's very important which carbon gets the hydrogen, which carbon gets the halogen. If you had that switched and put the bromine on the first carbon, I'd mark it totally wrong because you've shown me you haven't learned Markovnikov's rule. And in real life, having an atom like bromine on the wrong carbon could make something A, not work, or B, make it lethal and kill people. So it's very important where you want to put atoms should be correct. Now, let me remind you, a commercial from Dr. White, or I should say public service announcement. This is a general reaction. You need to memorize that. How do you do that? Write it down 5 times and say it. Double bond HX, where X is chlorine, bromine, or iodine. You break the pi bond, 1 carbon gets H, the other gets X, and it follows Markovnikov's rule. Because this is your roadmap that will tell our GPS that will help you do that on the test. And I'll put things on a test to let me know if you've opened up your notes. Please don't. All right, let's try another one. All right, here's the reaction. And again, the question is, Give the organic product or products. Now, first of all, do you see something different that's not carbon, hydrogen, or carbon-carbon single bond? Get your attention like that? And the answer is yes, a double bond. So everything else is going to come along for the ride. And as soon as I see that, this is all I think of. I'm reacting with HI. Oh, iodine is a halogen, hydrogen halogen acid. And remember, this has one pi bond and one sigma bond. You break the pi bond, one carbon gets H, the other gets X. Remember, X halogen can be chlorine, bromine, or, hold on, I keep on forgetting, you people, most of you can't read script, and I write script quicker than I can print, or iodine. And remember, this follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen from HX, and the other carbon gets the halogen. Well, now you got to use your high-level math skills. Here are the two carbons of the double bond. This has two hydrogens. This has none, 0. And which is the greater number? And time's up. Hopefully I'll pick 2. So the hydrogen will go to this carbon. Remember, the rich get richer, the poor get poorer. That has more hydrogens, it's going to get the hydrogen from here. The other carbon gets that, and you break the pi bond. Why? Because if you didn't, you'd have more than 4 bonds to carbon. Do you break carbon-carbon single bonds? No. So I have 3 across carbon plus this methyl group, CH3. I still have that. Notice I broke the pi bond, and this carbon will get the hydrogen because it has more hydrogens to begin with. This carbon will get the halogen. In this case, it's iodine. And I know there are 4 bonds to carbon, so I can put in my hydrogens. Now, if you want to move this up and make that CH3, you can't. You don't have to. Either way would be correct on my test. Would I tell you I'm this close to the person grading the test? Me. All right, I've been having all the fun. I've got to let you have some fun. And here's some fun for you. Give the organic product or products for the following. And for those who have your webcam on, thank you. I get to see real live students. My other class is for first year students, and for some reason, first year students never turn on their webcam. I don't know why, but they don't. I had 1 or 2 the first day. They saw everybody else had theirs off, and so I said, "Oh, I'm going to turn mine off too." Thank you, Christiana. Or is it Anna? Anna or Anna?
I usually say Christiana, but it depends on what you're more like what you normally say.
Well, ich spreche Deutsch, so Anna works for me.
Okay.
Did you know what I just said?
That you speak Dutch? Ik spreek een beetje
Oh,
Nederlands.
I speak German. Deutsch is German. And I do speak some Dutch because I worked in the Netherlands.
I speak very little Dutch. I've been working on it.
They were always amazed that because I know Hebrew, I can say certain sounds that Americans can't say. Quick timeout before we do this. One company, I would stay in The Hague, which is not how it's pronounced in the Netherlands. I don't know if I mentioned this, but I worked in this city. Have you heard about the cheese, Gouda? That's
Yeah, my friend Tim lives there.
I worked there I'd go there and I'd be in 2 weeks at a time, a couple times a year, sometimes 3 weeks. And it's pronounced by Americans Gouda. That's not how the Dutch pronounce a G. It's pronounced Gouda. And most Americans cannot say that properly. And the Dutch were always amazed I could. I said, because my Hebrew training. And there's a town, not a town, a beach right outside of The Hague, which is really Den Haag, Den, which is the Haag, Den Haag. And it's an important international city. The International Court is located there. And this name of the town, the beach, was used to identify German spies in World War II, because the Germans cannot pronounce it like the Dutch would. And the name of that beach is Scheveningen. But anyways, back to chemistry. Let me do this. You can party hard in The Hague or in Amsterdam, real good. Anyways, double bond. That's what difference. What are we reacting with? Hydrochloric acid. Chlorine is a halogen we show by X. For this reaction, X can be chlorine, which it is. It can be bromine or iodine. Good news, when I write my test, I will type Cl so you can see it. You don't have to. I just refuse, or not refuse. My brain and hand don't want to write that non-cursive. All right, you break the pi bond. Remember, there's one pi bond, one sigma bond. And you break the pi bond, sigma or single bonds you don't break. One carbon gets H, the other gets X. It follows Markovnikov's rule. And that is the carbon of the double bond with the most hydrogen gets the hydrogen, the other carbon gets the halogen. Do you break carbon-carbon single bonds? No, so I have 4 across, and I have this methyl group here. This carbon has 2 hydrogens, this has 1. Which number is greater? Isn't the math hard in my class? Oh, brutal. Hopefully I'll pick 2. So the hydrogen goes to that carbon, the halogen goes to the other. In this case, it's chlorine. There's 4 bonds to carbon. That's always going to be your friend on every test, which is why I always say it. And I put in the hydrogens. And that's how you, let's do one more. Now, first of all, any questions? And if
I do have a question. You put the chlorine on the bottom. Does it matter if you put it on the bottom or the top?
No, I usually organic chemists write on the bottom. If you were to write it on the top, I'd say, oh, that's different, smile, and mark it correct.
All right.
There's certain, I wouldn't even call it conventions, things that are passed down that, oh, he did it this way, I'm going to do it that way. And that's just the way it is. Now, I haven't told you this. Maybe I did. You know who the greatest of all organic chemists is, or one of the greatest? Mother Nature. And I'm going to have to tell you something personal. Mother Nature and Dr. White love rings. Students don't. Again, Dr. White, Mother Nature love rings. Students don't. In fact, my PhD thesis dealt with making a very complex ring system. And why don't students love rings? Well, here's the example. And I'll do this. All right. Everybody see the ring on the screen? Thank you. And you look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. You say, ooh, a double bond. And I have a double bond. Everything else comes along for the ride. HBr, ooh, bromine, halogen. X for this reaction can be chlorine, and in this case it is bromine, or iodine. And you break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule, which the carbon of the double bond with the most hydrogens gets the hydrogen, the other gets the halogen. Uh-oh. I don't see any hydrogens on the ring. What am I to do? Well, you know, there are 4 bonds to carbon. And if we look at this carbon right here, how many lines to that? 1, 2, 3, 4. 4 minus 4 is 0. If we look at the bottom carbon here, how many lines do you see to it? Otherwise known as bonds. I'll let you figure it out and then I'll tell you. And the answer is 1, 2, 3. So there are 3 bonds, but there should be 4 bonds to carbon. So 4 minus 3 equals 0. But brain freeze. I was looking up here and not thinking. That rarely happens. I almost did it again. Look down here, Dr. White. It's 1. So there's 1 hydrogen on the bottom carbon, 0 on the other. So you got to calculate that when you look at a ring for this reaction. Now, which carbon has the most hydrogens? Hopefully you pick 1. And therefore the hydrogen goes to this carbon and the halogen goes here. Now, do we break carbon-carbon single bonds? No. So I'm still going to have my ring. I'm still going to have the methyl group. Now, the hydrogen goes here, but we don't show it. The halogen goes to the other carbon, and that would be this carbon right here. And there it could be. Now, you could also have drawn it this way. And for this class, it makes no difference. Now, let's see if I was telling you the truth. I was, but let's still check. You never know. We started here, there was 1 hydrogen. Let's look at this carbon. How many hydrogens on that carbon? Well, count the bonds. 1, 2. 4 minus 2, because there's always 4 bonds to carbon, is 2. So now there's 2 hydrogen. We started with 1, we added 1, and we did add the hydrogen there. So that's how you use a ring with a double bond. And here's one for you to have fun with. 3 points, give the organic product or products for the following reaction. And hopefully those of you who are taking organic for the second time, finding it a lot more enjoyable and doable this time. Remember, if you need help, I have my office hour on Monday and Wednesday from 5. Now, one of the things I told my other class, and I'll tell you, if you would like me to change that on Monday or Wednesday to later time, that would be better for you. Email me and let me know, and I'll try and accommodate people because I can change it. Now you know why students don't like rings. When you're done, give me a thumbs up. Or, you know, in Zoom, or with your webcam, you can do a thumbs down too. Or I could do a generation gap. How many of you ever seen Our Gang with Spanky and Alfalfa? It was a serial show, used to be on TV, which originally started in the 1930s in the movies. And they had their high sign for their gang was this. All right, everybody done? Let's do it. We look at this molecule, what's different? What's not a carbon? What's not hydrogen? What's not a carbon-carbon single bond? A double bond. Everything else is going to come along for the ride. Reacting with hydrogen iodine. Iodine is a halogen we show by X. And X for this reaction can be chlorine, bromine, or iodine. You break the pi bond. Remember, there's one pi bond, one sigma bond, and each carbon gets something. The carbon with one gets H, the other gets X. How do you know which? It follows Markovnikov's rule, that great Russian organic chemist. And the carbon of the double bond with the most hydrogen gets the H. The other carbon gets the halogen. Oh no, it's a ring. We've got to count bonds to determine how many hydrogens. So I have these two carbons double bond. This one on top, how many bonds to that? 1, 2, 3, 4. 4 minus 4 is 0. So on this carbon right here, there's 0 hydrogens. We go to the other carbon. There's 1, 2, 3 bonds to it. 4 minus 3 equals 1. So this carbon has 1, which is the larger number. Remember, Markovnikov's rule is the carbon of the double bond with the most hydrogens gets the hydrogen coming in, which would be here. Now, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. If ever bend in a line as a carbon, I'll still have my ethyl group here, 2 carbons. The carbon right here will get the hydrogen. The carbon with no hydrogens will get the halogen, X, which in this case is iodine. And I know there are 4 bonds to carbon, and there you go. Now, you could have also written it this way. And that would have been the same thing. And that's how you do that. Any questions? Again, and I'm not going to sugarcoat it. Later on, I'll talk about sugar, but not now. And that was awful. I'm sorry. But anyways, you need to memorize this general reaction. And you do it by repetition. Flashcards don't work as well, especially I never liked them. All right, let's move on. Let's look at the addition of water to alkenes, which is also called hydration of alkenes. I'll never ask you on a test what is the name of a reaction, but I do use them. Now, let me rewrite this underneath a better way. When I made these slides, I was trying to be too fancy. Now, what this reaction is you have a double bond, remember, 1 pi bond, 1 sigma bond. And what is H plus? H plus, it means acid catalyst. A catalyst is something that makes a reaction go quicker, but is not consumed during the reaction. And H plus is the general way of writing any acid. Now, usually one acid used here is sulfuric acid, H2SO4. There's some acids that are used here you're not going to learn about this semester, like methane sulfonic acid and toluene sulfonic acid. But they all donate a proton, H plus, because an acid is a proton donor. By the way, a sidelight that I learned from someone years ago who's a biochemist, that most of your enzymes, which are catalysts, are just fancy acid catalysts. But anyways, here's water. Let's think of water this way. HOH. This is called a hydroxyl group. I'll never ask that on test, but I'll use that. So think of water as a hydrogen and hydroxyl group. You break the pi bond, one carbon gets the H from water, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogen gets the hydrogen, and the other carbon will get the hydroxyl group OH. Well, let's have some fun. And the question would be, give the organic product or products are the following. And while you're writing it down, I'm going to sneak some tea. And now if we look at this, what's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? It should get your attention like that. And we have a double bond. Everything else is carbon, hydrogen, carbon-carbon single bonds, which nothing's going to happen there. All the fun is always where there's something different. I'm reacting with acid catalyst H plus, excuse me, and water, getting all choked up over this, so exciting. Oh, that was awful. Sorry. And think of water as HOH. You break the pi bond. Remember, it has one pi bond, one single bond. One carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. Well, we got to look at the two carbons in a double bond and count hydrogens. Ooh, this is tough math. This has how many hydrogens? 2. This carbon has 1. Which is the greater number? And time's up. Hopefully, I'll pick 2. Do you break carbon-carbon single bonds? No. So I start with 4. I better end up with 4. Notice I broke the double pi bond. And here are my 2 carbons of the double bond, which are these 2 carbons. Which carbon has the most hydrogens? That one. That will get the H. This will get the hydroxyl group. The hydroxyl group counts as 1 bond to carbon. There should always be 4 bonds to carbon. And therefore, I can put in my hydrogens. And that's how you do it. Now, later on, I think in 2 chapters, you'll learn that a carbon with a hydroxyl group on it is called an alcohol. I think you might have heard that word before sometime. And there are many different types of alcohol, even though most people just think of one type when you say the word alcohol, unless they're organic chemists. And here's one for you to try. Give the organic product or products for the following reaction. 3 points each. And don't forget, later today, we'll be doing the second lab of the semester. Oh, it's going to be a lot of fun. Well, I see one person done. Two. And I better get to work because everybody's done. Thank you for all of you for letting me know. All right, what's different? A double bond. Remember, what's not a carbon-carbon single bond, carbon or hydrogen should get your attention immediately. And it did. So we have a double bond. Everything else just comes along for the ride, reacting with acid, H plus catalyst, and water. Think of water as H, OH. You break the pi bond. Remember, this is one pi bond, one sigma bond. One carbon gets H, the other gets the OH hydroxyl group from water, because water is HOH, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogen gets the hydrogen, and the other carbon gets the hydroxyl group. Well, now we got to use our high-level math skills and count hydrogens of the carbons of the double bond. This has 2. Oh, that has none. Which is the greater number? Hopefully you all pick 2. So do you break carbon-carbon single bonds? No. So I have 4 across. I still have this methyl group, CH3 there. Here are my 2 carbons. The N carbon, because of Markovnikov's rule, has more hydrogen, so we'll get the hydrogen from the water. The other carbon will get the hydroxyl group. And the hydroxyl group counts as 1 bond to carbon. And I can put in the rest of my hydrogens. And that's how you do it. Oh my goodness, time flies when you're having fun with Markovnikov's rule. It's time for a break. I'll see you in 5 minutes. I'm going to go check and see if the mailman came to my house. And I'll see you in 5 minutes. So take a break. I will. Time to get going. Welcome back. All right, let's get back to where we were working on. And that was the reaction of a double bond with acid and water. You break the pi bond, and one carbon gets the H, the other gets the OH. Remember, water is HOH, H2O, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other gets the hydroxyl group. Or another way of remembering is the rich get richer and the poor get poorer. And we're talking about hydrogens, not dollars. And the other gets the hydroxyl group. Now, let's see if you're up to one. Well, I'm so happy I mastered this tablet and I came up with the invention, not really invention, of using Microsoft Word as my whiteboard. Works out pretty good, doesn't it? Didn't know your instructor was a Zoom master. Oh, that was awful. I wonder if they have black belts in Zoom. A Shaolin Zoom master. And when you're done, give me a thumbs up. I think two of you are done. And we'll wait for number 3. And we're all done. All right, let's take a look at this. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? I'm going to say that a lot because that's how I look at molecules, a double bond. Everything else is just going to come along for the ride. So I have acid, catalyst, H plus, and water. Think of water as HOH. You break the pi bond and sigma bond, single bond, you don't. One carbon gets the H from water, the other gets the hydroxyl group OH. How do you know which? It follows Markovnikov's rule. The carbon of the double bond that has the most hydrogens gets the hydrogen, the other gets the hydroxyl. Oh no, we got a ring. We got to figure out hydrogens. And if we look at these two carbons, the top carbon has 3 bonds to it, but there should be 4. So 4 minus 3 equals 1. So there's 1 hydrogen there. The bottom carbon there has 4 bonds, 1, 2, 3, 4. High level math time, 4 minus 4. Hope we all got 0. Now, which of those two numbers is larger? And time's up. Hopefully you'll pick 1. So the hydrogen will go to this carbon. The hydroxyl group will go to the bottom carbon. You break carbon-carbon single bonds? No. Therefore, I still have my ring. I still have my methyl group. I did break the pi bond. And one carbon gets the hydrogen. That's this up here, but we don't show it. And the bottom carbon gets the hydroxyl group. And I could have written it this way, or for this class, this way. Either would be correct. And that's how you do it. Any questions? Now, it turns out it's quite useful to know how to make alcohols, because alcohols can react with other things to make things like the perfume you use. I bet you never thought of Perfume is very, and I mean very sophisticated, also very lucrative organic chemistry. So is cosmetics is very lucrative and very sophisticated organic chemistry. Now, I'd like you to do something right now, and that is think about where you are right now. 5 months ago, if you had seen this, would you know what to look for? Would you know how to approach this at all? Would you know about general reactions? Doesn't it feel good how much you've learned in our short time together? Shouldn't you be very proud of yourself? You should. See, organic chemistry is fun. It even puts a smile on your face. All right. Now, there are other reactions, double bonds. I only have 1 semester. I could go this type of general survey. I could do a 2 semester. I could do a 4 semester, but we only have 1. So I picked out certain reactions that I think are key. Remember, these general reactions are the building blocks, the tools organic chemists like me use to make molecules you use in your everyday life. And as we go on in the semester, you'll see where they are more and more. Let's move on. Now, let's talk about triple bonds. Alkynes is a triple bond. 3 lines tell you it's a triple bond. And here we have 2 pi bonds and 1 sigma bond. Excuse me. And it's an acyclic saturated hydrocarbon with 1 or more triple bonds. Triple bond is linear. That I'll never ask you on a test. This slide is just more informational, not something that would be on a test. Undergoes the same reactions as alkenes, double bonds, but now you have not 1, but 2 pi bonds to have fun with. And they undergo those same type of reactions. And we did the nomenclature. Remember, double bonds have an ENE ending, drop the ANE from the alkane, put ENE. Triple bonds, drop the ANE, put YNE. In triple bonds, there's no cis or trans. And also, I can't remember, it's been decades since I saw once, I think, a triple bond in a ring. You aren't going to see it in your lifetime. I haven't seen it. So don't worry about it. Now, let's look at the first reaction of triple bonds. If we take hydrogen and a triple bond, and there's something different there, bracket, excess, close bracket. Let's talk about that. Now, as you learn from a double bond, if you add a hydrogen and a catalyst, and the catalyst can be platinum, palladium, or nickel, PT platinum, PD palladium, Ni nickel. If you're in industry, you use nickel because the other 2, platinum and palladium, are really expensive. And you break pi bonds. Now, did I tell you organic chemists are lazy? We are lazy. And we don't want to balance equations when we don't have to. So how do we get around this? Because you got 2 double bonds, you need 2 molecules of hydrogen. And if you had more pi bonds or 2 pi bonds, you need more hydrogen. So here's what we do. Bracket, the letter X, the letter S, close bracket. This stands for shorthand for excess. And that means you've got all the hydrogen in the world to react with anything hydrogen can react with. Bracket, X, S, close bracket means there's excess hydrogen. You've got all the hydrogen in the world to react with whatever it can, and it does. So we have 2 pi bonds will break it. Each pi bond, each carbon of the triple bond gets a hydrogen. Since they're 2 pi bonds, each get 2 hydrogens. And that's why we need the excess so we don't have to balance it. And that's a common practice. Whenever you see bracket, letters X and S, close bracket, that tells you you have enough of that reagent or chemical to react whatever it could react with. So this is hydrogenation of an alkyne, a triple bond. And I'll do one, then I'll let you have some fun too. So we have this triple bond. We'll react it. Well, let's look at this molecule. I got ahead of myself. Sorry. All right. You look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen. Ooh, a triple bond. What are we reacting with? Hydrogen. Ooh, wait. Bracket, excess, close bracket. That means excess hydrogen. I got all the hydrogen in the world that can react with anything hydrogen can react with. Next, I have platinum, and that's a catalyst. And the catalyst can be platinum, palladium, or nickel. And what do? You have the 2 pi bonds, the 1 sigma bond. Do you break sigma or single bonds? No, no, no. Oh, that was a new way I said it. I don't think I'll use it again. You do it? No. That sounds more like it. And you break the 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. Let's try this one again. So it looks like a hydrogen. And this one gets its 2 hydrogens. So do you break carbon-carbon single bonds? No. So up here, I start with 4 carbons. I better end up with 4 carbons. I broke the 2 pi bonds, which you'd only see 1 line, not 3. And each one gets 2 hydrogens. And there you go. Now, one thing I might have mentioned, every problem I do for you in this class, like this, I will always write the general reaction underneath. Some of my best students I've ever had in Chem 170, you look at their test, under each reaction, they've written the general reaction. Some of my best students I've ever had in Chem 170, if you look at their test, they don't write the general reaction, but they have it up here. So it's your choice, but I will always write that underneath. Your turn. Give the organic product or products for the following reaction. Now, over the years, I thought of maybe I should bring a tape in or a digital recording of game show music. You know how they have when the contestants are thinking about the answer for writing it down at the end of whatever game show. You hear da 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 da. Nah. Well, I see 2 people done, and we'll wait for number 3. Thank you. All right, look for what's different. Ooh, a triple bond. And everything else is not different. Remember, look for what's not a carbon-carbon single bond, carbon or hydrogen atom, but we have a triple bond. We're reacting with hydrogen gas, and it's excess. That means we've got all the hydrogen gas in the world to react whatever it will react with. And palladium, Pd, is a catalyst. And the catalyst can be platinum, palladium, or nickel. And you break the 2 pi bonds, and you should know a triple bond has 2 pi bonds, 1 sigma bond, and each carbon of the triple bond gets 2 hydrogens. So do you break carbon-carbon single bonds? No. So I have 4 carbons across, and this carbon here has 2 methyl groups, CH3. Notice I broke the 2 pi bonds, and now each carbon of the triple bond gets 2 hydrogens. And I add 1 more here, add this, I'm done. Oh, let's do another one. Well, first, I'll let you take a look and see if you got it right. Everybody done? I have to watch out. I have the fastest mouse wheel finger this side or the other side of Mississippi. And here's one more for you to do. Give the organic product or products to the following reaction, 3 points each. And don't forget, if you haven't, turn in your lab that's due today, or make sure you get it in tomorrow. All right, we'll wait until everybody's done. All right, time to get to work. We look at the molecule, look for what's different, what's not a carbon-carbon single bond, carbon hydrogen, ooh, a triple bond. Remember, that's 2 pi bonds and 1 sigma bond. We're reacting with hydrogen and ooh, bracket X, S, close bracket, that's excess. That means you've got all the hydrogen in the world that hydrogen can react with. And we have nickel, which is a catalyst for hydrogenation, which is what this reaction is. And it could have been platinum, palladium, or, as in our case, it is nickel. And you break the 2 pi bonds, and each carbon of the triple bond gets two hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 carbons. I better end up with 6 carbons. The 2 carbons of the triple bond, notice I broke the 2 pi bonds, so there's only 1 bond or line between it. Each one gets not 1, but 2 hydrogens. And I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's how you do it. If you wanted to make this CH2 and CH2, you can. You want to leave it like that, you also can. All right, let's move on. Uh-oh. Let me try something first. That's not what I want. No, that didn't do it. How many of you are familiar with CCleaner? It's a really great free product download. I've got to close my Word documents and open them up again. All right, I'm back in action. All right, everybody see halogenation of an alkyne? And here I have it written this way. A better way is, let's look at a triple bond. Remember, it has 2 pi bonds, 1 sigma bond. And if we react it with halogen gas, remember X can be fluorine, chlorine, bromine, or iodine. But now we have 2 pi bonds, and once again, I don't want to balance things. I'm a lazy organic chemist. So I'll put bracket XS, close bracket. Whenever you see bracket XS, close bracket, that means you have all the reagent, in this case chlorine or bromine or fluorine or iodine, to react whatever it can react with. And you break the 2 pi bonds, and each carbon of the triple bond gets not 1, but 2 halogens. So again, the 2 pi bonds are broken. The excess right here tells you you've got all the halogen in the world that will react with anything it can react with. In this case, it's each carbon of the triple bond gets not 1, but 2 halogens. And why would you want to do that? Well, one thing is the more halogens you put in a molecule, you make it more flame retardant. And those are chemicals used to inhibit things like your sleepwear from catching fire easily, which is a good thing, especially among children's sleepwear. Does everybody see my whiteboard on there with the reaction I just wrote? Thank you, Nacio. All right, I'll do this one, then you know I'm going to share. And the question is, give the organic product or product for the following reaction. 3 points each. And what do we have that's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? A triple bond. Remember, that's 2 pi bonds and 1 sigma bond. Wow, that's one of the best pi bonds, 5 characters I've written in a long time. And remember, halogens are abbreviated by X, halogen gas, X2, and we have XS. Remember, that means you have all the halogen in the world that will react with anything it can. Remember, X can be fluorine, chlorine, bromine, or iodine. And you break the 2 pi bonds, and each carbon of the triple bond gets 2 halogens. Do you break carbon-carbon single bonds? No. So I have 3 carbons. I broke the 2 pi bonds, which is why you only see 1 line. And then here are my 2 carbons of the triple bond, and they each get 2 halogens, and the halogen is chlorine. And each chlorine counts as a single bond. There should be 4, yes, 4 bonds to carbon. And I'll make sure that happens by putting in hydrogens. And that's how you do it. And here's one for you to do. And when you're done, don't forget, give me the thumbs up. Or if we were face to face, I'd say smile when you're done. I do that to the class. I see a lot of smiling faces. All right, I think everybody's done, so I better get to work. If we look here, what's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? A triple bond. And just to remind you, it has 2 pi bonds, 1 sigma bond. What's fluorine gas, F2? That's this halogen. Remember, X can be, and it is fluorine, but it could have been chlorine, bromine, or iodine. And you break the 2 pi bonds. I did. That's why there's only 1 line. And each carbon gets 2 of the halogen. So I have 2, 4 across plus 1, 1, 2, 3, 4 plus the 1. Here are my 2 carbons of the triple bond, which are these 2 carbons. Each one gets 2 fluorine. And I know there, oops, I almost forgot to finish with the fluorines. And I know there are 4 bonds to carbon. Each fluorine counts as a bond. And I'm done. And that's how you do it. Any questions on halogenation of a triple bond? Now, there are a few more things I want to talk about that I didn't have in the slides, but I'll do it the old-fashioned way. I'll draw it on the board. Now, let's look at the following molecule. And most of the time I stay away from this, but this is a good example of functional group chemistry and how important it is, and really how beautiful it is. Now you really know I'm an organic chemist. Now, when you have a double bond in a molecule, well, first of all, let's look at this molecule. What's different? What's not a carbon-carbon single bond? What's not carbon or hydrogen atoms? And if we look here, ooh, a double bond. Wait a second, a second double bond. Now, when double bonds are separated by more than one carbon, then they react like they're alone. Or when they're separated by one or more carbons, they react like they're alone. Even more than one is better. When they're not separated, that's called conjugated. And that's for a 2-semester organic, which this is not. So notice they're separated by more than one carbon. So each double bond reacts like it's alone. But because I have 2 double bonds, I would have to balance things. But no, I'm lazy. I just say there's excess hydrogen. And that just means there's all the hydrogen in the world that anything can react with. Well, what can a double bond do with hydrogen and a catalyst? Where the catalyst can be platinum, palladium, or nickel. You break the pi bond, and each carbon gets a hydrogen. Do you break carbon-carbon single bonds? No. So I have 6 carbons here. I'm going to end up with 6 carbons. Now, this first double bond, I broke these 2 carbons, and they each get a hydrogen. And these 2 carbons here, I broke the pi bond, and each gets a hydrogen. I know there are 4 bonds to carbon. And I can put in my hydrogens. And that's what happens. So whenever you have a double bond separated by 1 or more carbons, they react like they're alone. Hold on, everybody got a copy down that wants to get a copy down? I see a couple heads going up and down, so that means I can move forward. Now, let's test your knowledge using that same concept. This is a little more tricky. Let's see if you're up to the challenge. If you take that molecule and react it with HBr, but excess, which means you've got all the HBr in the world that can react with anything HBr can react with, what would be the organic products or product for this reaction? Hint, go back and look, Markovnikov addition. And when you're done, give me a thumbs up. Or if you've given up, well, I hope you haven't, give me a thumbs down. Oh, bad Dr. White. I'm sorry. Shouldn't have said that. Ooh, no violence in my classroom. All right, everybody done? Let's take a look at this. Look at a molecule. Look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen. Ooh, a double bond. Wait, there are two of them. And what are we reacting with? HBr and excess. The bracket X S close bracket. This tells you you've got all the HBr in the world that can react with HBr. What's HBr? I've got a double bond. Actually, I got two of them, but I'll look at one at a time. HX. X can be chlorine, bromine, or iodine. And what happens? You break the pi bond, and one carbon gets H, the other gets X, and it follows Markovnikov's rule. And do you break carbon-carbon single bonds? No. So I start out 1, 2, 3, 4, 5, 6. I better end up with 6. Now, let's look at this first double bond. This carbon has 2 hydrogens. This one has 1. Which one has more hydrogens? Hopefully you pick that one. Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen. The other gets the halogen. That's bromine. Let's look at this carbon. How many hydrogens on each carbon double bond? This has 2. This has 1. Which has more hydrogens? This one. Therefore, the hydrogen will go there, and the halogen will go to the other carbon. And now I know there's 4 bonds to carbon. I can put in the rest of my hydrogens. Now, when it's conjugated, there's a whole bunch of other rules and mechanisms you have to learn. We don't do that in my class. Okay, I'll wait until everybody's finished writing this down. And you apply the same reactions you've learned, but now we've got 2 separate areas that will happen. Everybody done copying? Okay. Now, there's another thing I'd like to talk about, and that is nobody is ever going to pay a PhD chemist or even a master's or even a bachelor degree chemist in organic chemistry to say, well, if I react this and this, what am I going to get? They're not going to pay you. What they do pay people like me, and I've been paid a lot when I worked in the chemical industry, is how do you make a molecule? And at my level, it gets even more complex. How do you make a molecule with these properties that we can do in our existing plant equipment? But for this class, we will last to. And the question would be, and I'm going to simplify it for you. And this is called synthesis. Synthesis is a fancy word to make. And I am by training and by experience a synthetic organic chemist. I make things. So the question is, what would you react with chlorine gas to make this molecule? Well, how do you do this? Well, you look at the molecule you're trying to make and say, what's different? Ooh, what's not carbon? What's not hydrogen? A chlorine here and a chlorine here. And you've got two chlorines. Remember, we call that X on adjacent carbons. Adjacent means next door to each other, connected. And we're reacting with halogen gas. And what do we react? Well, a double bond. Take a double bond, react it with halogen gas. Each carbon of the double bond gets a halogen. And if we back up, do you break carbon-carbon single bonds in this reaction? No. And you're not adding any here either. So we end up with 3. I better start with 3. Now the 2 carbons with the halogen will be the 2 carbons in the double bond. So I'll put my double bond there. And now I know there are 4 bonds to carbon. If you notice this molecule, if I react with chlorine gas, I'll make the molecule I'm trying to get. Why don't you try one? What would you react with bromine gas to make that molecule? And this is the fun part of organic chemistry. But I'm quite biased because I'm a synthetic organic chemist. And we'll wait until everybody's done. All right. So if I look at this, how do I determine what do you react with bromine to make this compound? Well, I'll look for what's different, what's not carbon, what's not Woo, two bromines, and they're on adjacent carbons, one next to each other. And what do we react with a halogen gas to make that? A double bond. And X can be fluorine, chlorine, bromine, or iodine. In this case, it's bromine. Well, to break carbon-carbon single bonds, or have I added any carbons? No. So I end up with 6. I better start with 6 and the same structure, 4 and 2 carbons here. Now my 2 carbons with the halogen are these 2 carbons, which will be these 2 carbons double bond. Well, if it's these 2 right here, which are these 2, then there'll be a double bond between there. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And I'm done. Now, at least at this point in time, the Supreme Court of the United States has outlawed cruel and unusual punishment to students. I'm being facetious, but it sounds good. And these are much harder than what's the organic product or product problems. On test 1, I will only give one of these. Give the starting material. That's the type of question. On test 2 and 3, I usually put 3 or 4. But the bulk of the problems are the other ones we've always done. This is harder, but this is the best part of organic chemistry, the fun part, but it is challenging. And with that, it's time for a break. Well, time flies when you're having fun with triple bonds. And with that, let's take a 5-minute break, come back at 2:50. We'll do a little more lecturing, then we'll do the next lab. I'm back. All right, I was showing you synthesis problems. Remember on test one, which is going to be postponed by 1 week, I will only do one synthesis. Now, if you look at the practice problems, you say, you don't have any synthesis problems. Well, all you have to do is take any of the practice problem answers, put your hand over the starting material, and you have a synthesis problem. Again, go to the practice problem answers, take any one, put your hand over the starting material, and now you have a synthesis problem. But let's do one more. These are fun. What would I react with HCl to make that molecule? Oops, forgetting a hydrogen here. And, oh, excuse me, there you go. I'll give you a big hint, Markovnikov's rule. That was nice, Dr. White. Fully on you. See, I even keep it clean in my class. So far, nobody's ever given me the raspberry. You know what that means? I think some of you do. Uh-oh, I'm doing what my father told me not to do. That was, don't tell a kid not to shove peas up his nose with his knife. And we'll wait until everybody's done. I see 2 people are done. We'll wait for number 3. All right, let's take a, how do we do this? And the question would be, maybe even 5 points, 4 or 5 points, because there's only going to be one on test 1. And sometime you might see in the future, and probably won't be this, because there's only going to be one, give the starting material or materials for that. So what do we react with HCl, hydrochloric acid, to make this compound? Well, how do you do that? You look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen atom should get your attention like that. And, oh, we've got a chlorine on a carbon. But I'm reacting it with HCl, so I got to find somewhere to hydrogen. Oh, an adjacent carbon has a hydrogen. And what do we react? And if we look at this, we can say, well, chlorine is a halogen, adjacent carbon is hydrogen, HCl is HX. Remember, X for this reaction would be chlorine, which it is bromine, or iodine. And what do you start with? A double bond. And what this tells you is one of the carbons of the double bond has an H start, the one that, let me back that up, north, north. That's like if you take a tape deck and run it backwards. But the carbons with H and X have to be the carbons of the double bond. The carbons with the hydrogen, the halogen, adjacent, have to be the carbons of the double bond. Which are these two carbons? Do you break carbon-carbon single bonds? No. Did we add any carbons? No. We ended up with 4 across. So we end with 2 methyl groups. So we better start with that. And now the 2 carbons of the molecule with the hydrogen and the chlorine adjacent will now be the 2 carbons of the double bond. And we know there's 4 bonds to carbon. I'll put in the hydrogens. And that's how you do it. Now, let me show you something very important. What if you said, well, one of the carbons has the chlorine, is the carbon double bond, and I'll make this carbon the other one. And I'm going to do this in red because it's wrong. How do you know it's wrong? Look at that carbon right here. How many bonds do you see there? Count them. 1, 2, 3, 4, 5. No way. If you find a way to make 5 bonds to carbon, let me know, because we'll be rich beyond our wildest dreams. And for me, that goes beyond having my own Ferraris, Lamborghinis, island in the South Pacific, and fighter jets to play with and go out and fly around, have fun. That's beyond that. It doesn't happen. So remember, when you're drawing structures, make sure your carbons only have 4 bonds to it, because this right here tells me it's wrong, because there are 5 bonds to this carbon. No way. And why am I showing you this? Because on test 1, 2, 3, 4, and the final, if students had looked at what they wrote, structures, about 60, 70% of them would realize that can't be right. I've got 3 bonds to carbon, or I got 5. One time I saw twice 6 bonds to carbon. Boy, did I start laughing. It took me a while to stop laughing before I marked it wrong. Because you can only have 4 bonds to carbon. 4, 4. All right. Now, we have finished up chapter on alkenes and alkynes. And guess what time it is? I gotta practice that. It's time for a new chapter. And this new chapter is quite exciting. But before we do that, I better open it up. Let me close this. Let me go here. Let me show it to you. All right. Everybody see aromatic compounds on your screen? Now, this chapter deals with aromatic compounds. And these are so important There are wars fought over these compounds. Yes, back in the 13th, 14th, 15th, 16th, and 17th centuries, great wars were fought over aromatic compounds. Now, why are they called aromatic compounds? Because they are originally organic molecules isolated, meaning they come from spices and herbs. And that was a great important thing back in the Middle Ages. Why do you think Columbus came to America? Because he made a mistake or thought he was going to find a shorter route to India to get aromatic compounds, spices, because you could make a lot of money. Now, I should tell you, a lot of the driving force in science, especially organic chemistry, is how can you make some money? And it's still a driving force, and there's nothing wrong with that. Well, aromatic compounds, an example, one of my favorite is vanillin, which is from vanilla extract. I don't know about you, but I love vanillin, the taste and frosting. And how many of you are familiar with cream soda? Years and years ago, that used to be called a vanilla phosphate. You went into a deli or a good restaurant where they actually made it right there on the spot. But anyways, those are the good old days, whatever that means. All right, now, when we talk about aromatic compounds, they're very stable. They have very unusual chemical properties, especially their stability. They don't react when you don't want them to react. And many have, and this should be C6H5, not H6, ring in it. And this is an aromatic compound. Now, one of the things I talk about right now, you can buy it a lot of places. That's not what I wanted to do. All right, everybody see Napoleon's buttons and 17 molecules that changed history. And it's a great book. I should buy a copy, or I should get a copy for my Kindle. And every couple of years I reread it. I get it from my local library. I probably can get it electronically from them. So I don't even have to pay for this. But anyways, these two French authors, two women, did a great job. And why is it called Napoleon's buttons? Well, as you all know, hopefully you know from history, when Napoleon invaded Russia with the winter in Russia, it defeated his army. That was his first defeat, and that led to his downfall. Well, one of the rumors were, why did his army lose? Well, the buttons they had on their coats were made of inferior metal that in the super cold weather, winter in Russia, they fell apart, broke apart. It's called friable. Well, this has a number of molecules, and most of those are organic molecules, and a number of them are aromatic molecules. Now, when you talk about aromatic compounds, if you're an organic chemist, immediately you think of, by the way, switches off on this slide, one of the greatest of all organic chemists, Kekula. And Kekula was, now we call it Germany, I think it was Austria then, or I forgot, chemist. And he was the first one to figure out the simplest compound, aromatic compound, is called benzene. 6 carbons, 6 hydrogens. And nobody could figure out what was the structure. How did it look? And Kekula was the one who did that. He proposed the reasonable structure, really the solution for benzene. Now, that alone would be a lifetime achievement to do that alone, but he did a few other minor things. He was the first one to recognize there should be 4 bonds to carbon. That's a lifetime achievement. He was also the first one to recognize that carbon atoms can be connected together by chemical bonds, which, like you saw in propane, butane, and that, to make chains. And that's a lifetime achievement. Now, if you talk to an organic chemist and say Kekula, they'll know about benzene, and they'll also remember his snake dream. Snake dream? Well, years later, and he came up with the structure of benzene when he was very young, but years later, when he was in his 60s or 70s, whatever, someone at a symposium asked him, how did you solve the structure of benzene? And he said, the night before I came up with the idea, I had this dream. And the dream was a snake chasing its tail and finally grabbing on and biting onto his tail and going in a circle, just holding on to its tail. And that gave me the idea for benzene. And all organic chemists, if you're a good organic chemist, know his snake dream. Again, switches off for this slide. Now, as you see on here, see the postage at Calcula? Great beard. I have to keep mine short because if I ever go into chemical plant, which I sometimes do, if I have to put on a gas mask, a beard like that would break the seal and I'd be dead. So that's why I keep it short like this. And if you notice, it's from DDR, and that's Deutsches Democratic Republika, otherwise known as East Germany, which is no longer. And this is a 25 pfennig, 25 cents stamp issued in 79. For a number of years, I told students, if you see one, let me know, I'll buy it. About 3 or 4 years ago, one of my Chem 170 students, I saw that on sale on eBay. I went there, yeah, and I bought 2 of them because they were cheaper than I ever thought they would be. And he is one of the greatest of all organic chemists. And if you notice right next to him, there's his structure for benzene. Now, benzene, we have what's known as resonance. Resonance means you move electrons, switches off on this one. And I used to put brackets, you don't really have to. It exists in either form. And the double-headed arrow is different from equilibrium. This shows there's resonance and the electrons can flow either way. And it happens at the same time. And this is because the p orbitals in benzene double bonds overlap to form a ring or a cloud above or below the plane. And benzene is flat, unlike cyclohexane, switches totally off. And it looks like this. Each carbon of the double bond in the pi orbital or pi bond has an electron in what's called the p orbital. That's in blue. When they all hold hands, how many of you have ever played Ring Around the Rosie when you're a little kid? Think about the words of that. That comes from the Black Plague. Ashes, ashes, we all fall down, if I remember correctly. But anyways, back to organic chemistry. By holding hands, it makes this compound extremely stable and unreactive. And it's called an aromatic compound. Now, switches off, aromatic compounds determine if it's aromatic or not. It's cycloatomic, meaning it's got a ring or rings, and it has 2n plus 2 pi electrons that are conjugated. N is a whole number. In benzene, N is 2. That will never be on test. Well, someone years ago told me they saw something like that on an entrance exam for nursing or something else, that the question was, which of the following is the aromatic compound? Well, you look for 2n plus 2 pi electrons. But switch is totally off, and I'll never ask this on a test. But now switch is on. Here's the structure for benzene. Now, there are two structures, actually 3 ways you can draw benzene. Now, IUPAC, in their infinite wisdom, the name benzene has been around for eons. And they said, well, we're not going to get organic chemists to change and call it something else. So we'll just say the IUPAC name is for benzene. Now, it has a 6-membered ring and 3 double bonds that are conjugated. Conjugated is alternating single, double, single, double, single, double, double, single, double, single, double, single. Now, this is one way of drawing it. Here's the other resonance form. And all I've done is move the electrons like this. And you get this form. And these are called Kekula structure, which I'll never ask on a test. Now, as you saw in the picture, you had the pi bonds holding hands, and it looks like a donut. If you were looking at above, you could draw it this way. And this is called the localized pi bond. Any one of these, A, B, or C, if I asked on a test, draw the structure of benzene, would be correct. Now, in class, I'm always going to draw it A and B. Why? Somehow I decided A and B look a lot cooler than C. Dr. White likes to be a cool dude. So if you write on a test the structure delocalized pi like C, I'll give that for full credit. But in class, I'll always do A or B because I just think it looks cooler because I like to be cool. All right, I think this is a good time to stop and start the lab. So let me close this. Let me open this, go here, go to the lab. Come back here, go like this. All right, everybody see alkanes and alkenes on your screen. If we were face to face, I'd be reminding you hydrocarbons like these are flammable in a lab, organic lab. We never use matches, lighters, or Bunsen burner. Never. So you'll have a fire, and we don't need that. And I would also tell you how to dispose of the waste. Now, as I said, I wrote these labs when I inherited a Chem 170 because I had to do a lab within an hour and 50 minutes and make it challenging and not spend a lot of money, which is quite interesting. So what I did was the first part, I'd have students smell some of these chemicals. How many of you have ever smelled gasoline at a gas station? Well, those are things, and you know what it smells like. Now, one interesting thing about odors, and later in the semester, one of the most difficult problems I had to solve dealt with an odor in a product we made or our customer made, and about $65–70 billion a year was on the line if I didn't solve that problem. Boy, that was a lot of pressure. I did. But anyways, I'll talk about that later. And for here, Dr. Daly, who's the lab manager at ECC, used to be I'd have students rip paper towels, put a little chemical on there, and go like this underneath their nose, never stick the paper underneath. That's the proper way to smell things. But once he got hired as a lab manager, he also was a part-time faculty like me too. He did things that made my life, my students, so much easier. We had 2 by 2 inch pieces of paper towel he had cut up, and you put some of that and you smell it. Now, since you're not going to do that, I put in what it smelled like. Now, notice in this table, draw the structures underneath the name. In this table, I'm asking you, part of the lab, draw the structure for octane, hexane. Now, notice I don't have a number for octane. Depending what we have in the stock room, might be 1 or 2. Let's make that 1 octane. And then limonene and naphthalene. Now, let's move on to part 2. Now, one of the things I did in these labs was I used some of the old, before we had electronic equipment, to analyze things like spectrophotometers or nuclear magnetic resonance spectrophotometer. The chemists from the 1800s up to the early 1900s had color tests. And color tests helped you understand or find out, was this sort of functional group in a molecule? One of the famous ones is you take a double bond, react with halogen, you break the pi bond, and each carbon gets a halogen. Now, the test involves bromine. If you take a double bond, and these molecules are usually either clear, no color, or slight yellow. Now, bromine in solution is a red, brown color depending on the concentration of the solution. If you have a double bond, you'll react it to form this compound. And this is also clear or slight yellow. Now, industrial chemistry, we have different scales for measuring colors of liquid, which I've worked with, and that would be about a level bond 0, or no, Gardner 0 or 1, which you don't know what I'm talking about. And I could also use APHA color, but I don't. So if you have a molecule and you add bromine and it doesn't turn red-brown, that means the bromine has reacted, and that tells you you have a double bond. And one of the nice things about this lab is you find out, is Dr. White lying to you? Well, here, since bromine is very dangerous in solution, and years ago I had a student who got in an accident, and somehow he got bromine on the back of his neck. I washed it off quick enough so it really didn't cause any serious damage, but I still sent him to a doctor. I do this test. And what I'll do is, in a test tube, I'll have small amount of the hydrocarbon, I'll add some bromine, I'll mix it up, and then you don't have to wait 5 minutes. I'll hold it up and say, what do you see? And when you do that, if you have cyclohexane, it goes red-brown, no double bond. Hexane, clear. Well, it's got a double bond. Let's make this again 1 octane. And then limonene stays clear. Now, to make it fun, I have 2 unknowns. And if you add unknown 1, you add to the bromine solution, it stays clear. If you add unknown B and bromine, it goes red-brown. And later on, I'll show you some questions. But when it stays clear, there's a double bond. When it goes red-brown, no double bond. Now, the last one is another test for measuring or determining is there a double bond in the reaction. Take a double bond, react with a potassium permanganate solution. It will oxidize the double bond. Each carbon double bond gets a hydroxyl group. This is a reaction I didn't talk about in the lecture, but I'll use in the lab. And that reminds me, listen carefully. Anything we do in the lab, I will never put on its hourly exams or the final. Those are concepts I cover in the lecture, not the lab. I keep them separate. Also, good news, I don't believe in lab quizzes. Nah. I have lab reports, and that keeps the lab fun. But you got to hand them in. So don't forget to hand in your lab report that was due last week. Now, let's go to my whiteboard of this reaction. Now, if you have a double bond in a molecule, this is still clear or slight yellow. I mean, if you have a lot of double bonds, it could be worse, like a carrot color, but and potassium permanganate, KMnO4, is a purple color solution. It's a solution in water, and you put a little acid in there. Purple. Now, if it reacts, it breaks the pi bond. Each carbon of the double bond gets a hydroxyl group. And then this is called an oxidation reduction reaction. This is oxidized, this is reduced, and you get manganese dioxide. And MnO2, manganese dioxide, the best way I can describe what it looks like is a muddy brown color. If you've ever been to parts of the United States with reddish brown dirt, or even near Chicagoland, and you put water on there, it looks that muddy brown color. Well, that's what MnO2 looks like. So if you mix potassium permanganate solution with a compound and you see a muddy brown, that tells you you have a double bond. So in this lab, we take and react certain chemicals. And what we'll do is in a test tube, you'll add about 10 drops of the dilute KMnO4 potassium permanganate solution. And this should be that subscript. And then add 5 or 6 drops of the alkane or alkene to be tested. You mix the tube, and I'm going to show you something in a second. Wait, and you don't have to wait 10 minutes. I usually tell the students, wait about 2 minutes. And then when you're done, put it in the proper waste bottle, which I'll tell you, and you repeat steps A through E through the products below. Now, one thing I forgot to do up here, you should watch this YouTube, and it's really exciting. Well, I'm an organic chemist. I think it's exciting. It shows how quickly that color change happens when bromine reacts with a double bond. And then here, I have a YouTube you should watch, which shows what happens, that muddy brown color, when you mix potassium permanganate solution with a double bond. Now, here again, you would be reacting the following. And let's make this 1-octene again. And now, cyclohexane stays purple, no double bond. 1-hexene, ooh, and you would have seen this in the lab, you'd see in the test tube would be muddy brown. And double bond. Same thing with octene, limonene, you already looked up earlier the structure. And then we once again have unknowns A and B. Remember, muddy brown, double bond, purple, no double bond. Now, for these questions, Please use your experimental results to justify your answers. Where I ask you to justify something. Here I ask you to draw the structures of the following compounds. And you can find this on YouTube, what am I saying? On Google. If you don't know the structures and how to do IUPAC names, you should for everything except the last two, limonene and naphthalene, which I think I talked about. And then here's some questions. What's the reason the color dilute KMNO4 becomes muddy brown? And show it with a general reaction. Then go back and look at the video if you didn't take good notes. And here I have some others. And if we were face to face, when I was talking about unknown A and B, I'd say the district attorney of Kane County, Elgin is in Kane County, has come to us and say, he's got two compounds. He has to know, does it have a double bond or not? And if he does know which one has the double bond, which one doesn't, he can convict a heinous criminal. I'll let you put in the think about which crime you'll call heinous of the following crime. And so it's your job to find out. And I'd say that in class, and really that's what I'm asking in question 4. And with that, we're done for today. We're done for the week, unless you need to come to my office hour tonight from 5 to 6:15. Now, as I mentioned to my other class that I teach at College of DuPage, if you can't come to the 5 o'clock office hour, let me know, and I can make it later on Monday and Wednesday. I might even be able to sneak it in Tuesday afternoon or Tuesday night. Thursday and Friday, I'm tied up. Not that kind of tied up. Oh, that was awful. But anyways, if you need another office hour time, let me know, because I'm here to help. And if nobody shows up when I have it, well, maybe I need to change the time. And with that, don't forget, lab you do last week, get it in. They're easy points. Today's lab we just did is due next Wednesday. You can hand it in anytime in the assignment area, but do it. And with that, remember, test 1 is postponed by 1 week, not the 14th. I'll send out an email announcement today or tomorrow, probably tomorrow, that it will be postponed. And with that, I'm done. And with that, I will say, Gehen gesund. I stole that from Granny Beverly Hillbilly. Bye now. Have a great rest of the weekend. I'll either see you in my office hour later today, or I will see you on Monday. Gehen gesund. Bye.